What if the life you're living right now isn't the only one? Somewhere, just beyond what you can see. There could be countless versions of you, some standing where you didn't, some saying yes when you said no, some living lives that feel impossibly far, yet are born from the same quiet choices. For decades, scientists and storytellers have wrestled with a question that seems more like wonder than fact. Does every moment split reality? From early Greek philosophers to modern quantum experiments and the mysterious cold scars in the sky, evidence keeps whispering that our universe may not be alone. Join us as we travel through hidden physics, daring expeditions, and the human longing to know what lies beyond one single road, a journey that could change how you see every breath you take. Imagine. Long and quiet, with doors spaced evenly on either side, each one shut and unmarked. Now imagine that behind every door is you, but not quite you, a version who turned left instead of right, who spoke a word instead of swallowing it, who stayed when you walked away. The picture begins softly, like light leaking under the cracks of those doors. It does not rush in with heavy theories or complicated names. It begins with a feeling you already know, that small tug when you wonder what might have happened if you had chosen differently. In 1957, a young American physicist named Hugh Everett III tried to describe that feeling in the language of quantum mechanics. He was not dreaming of science fiction or parallel lives when he wrote his paper at Princeton. He was trying to solve a quiet problem at the heart of physics. What happens when the invisible waves that guide particles collapse into the single, solid reality we see? At the time, almost everyone followed the Copenhagen interpretation, the view shaped by Niels Bohr and Werner Heisenberg, which said that before we look, the world is a haze of probabilities. But the moment we measure or observe, one outcome becomes real, and the rest vanish. Everett, patient and careful, thought that was too sudden, too magical for a universe built on rules. Instead, he imagined that the wave does not collapse. It simply keeps going, branching into paths we cannot follow. Every time a quantum event could go one way or another, the spin of an electron, the travel of a single photon, the universe splits quietly. One version of you turns right and lives a life built on that right turn. Another version turns left and lives a life built on that left turn. Both continue. Both are real. Everett's idea was not welcomed with applause. In 1957, he defended his thesis and faced skepticism that felt more like dismissal. The giants of physics were used to a world that, though strange, still snapped into place when someone looked. Many thought Everett's many worlds was unnecessary and unprovable. His work was published, yes, but then largely set aside. His vision of branching universes folded into a few obscure journals and conference notes. He left academia not long after, working for the Pentagon on nuclear strategy, while his idea drifted quietly in the background of physics for decades. But though few noticed then, the seed was planted. The image he gave us is simple enough to hold in the mind. Single reality splitting into countless shimmering hallways, with each event too small to feel. When you step off a curb and a car misses you by inches, perhaps in another world it did not. When you send a message to someone you love and they answer, perhaps in another world they stayed silent. These worlds do not touch, and yet they are born from the same thread. Everett said we experience only one because the others, though real, become separate by decoherence, a quiet, almost ghost-like fading of quantum connection that keeps their histories from interfering with ours. You do not need to picture equations to feel what this means. You only need to imagine a single coin flipped in a small kitchen on a quiet morning. Heads, and a conversation begins. Tails, and it never does. Physics says the coin does not simply land one way. It lands both ways, but you will only ever know one. The rest go on without you. They are not ghost worlds. They are as solid as this one, just beyond the reach of your senses. Everett believed that reality itself is this great, endless branching. In the years since his lonely paper, experiments have not proved the many worlds outright. No one has seen across the hall, but quantum theory has grown stranger in ways that lean toward him. Each time physicists test entanglement and find nature refusing to be local and tidy, Each time they watch a particle act like a wave until someone tries to catch it, Everett's picture feels less like fiction. It is as if the universe itself is whispering that it is bigger than the slice we stand in. So picture again that hallway. Each door, a quiet life, yours and not yours, lined up in endless patience. You will never open them. No one can. But knowing they might be there changes the way the single corridor under your feet feels. It makes the floor seem less final, the light less small. And it is here, in this soft and unnerving thought, that the multiverse begins not with flashing machines or glowing portals, but with one man in 1957 refusing to accept that the wave of reality dies just because we look. Long before wires hummed with electricity and screens carried the weight of the world's questions, men and women looked up at the night sky and tried to guess what waited beyond their sight. In the dark of Greece's city-states, in small courtyards and stone classrooms, philosophers let their thoughts wander past the familiar hills and seas, searching for the very first shape of reality. Among them was a man named Democritus, born in the city of Abdera, around 460 BCE, who spent his life imagining what the world was made of. To him, the endless changes of nature, fire swallowing wood, rivers breaking banks, stars appearing and fading, hinted that everything was built from tiny, unseen pieces he called atomos, meaning uncuttable. These atoms, he said, moved in the void, colliding and swerving, building and breaking worlds without end. In his mind, the cosmos was not a single room, but a vast field scattered with countless worlds. Some like ours, some strange beyond imagining. His vision was daring for its time. To say there might be other worlds was to stand apart from the comforting idea of one, ordered cosmos with Earth at its center and the gods looking down. Yet Democritus insisted, if the void is infinite, if atoms move forever, how could they not gather into other suns, other lands, other skies? The words he left were sparse, often carried to us secondhand by later writers. But they burn quietly through the centuries. Worlds without number, some without sun or moon, some destroyed as others rise. To hear him speak across millennia is to feel a small echo of today's talk of multiverses, fragile, daring, but stubbornly alive. His teacher, Leucippus, shared these thoughts, and later Epicurus would carry them forward in the 4th century BCE, arguing that nothing in nature stops the birth of other worlds. These thinkers did not have telescopes or equations. They had patience in night skies and the will to imagine beyond their city walls. While poets sang of gods and underworlds, these early atomists thought, instead of infinite matter, moving without favor or plan, their other worlds were not mystical heavens, but natural outcomes of the same rules that built ours. For centuries, their ideas would drift in and out of fashion, buried by Aristotle's firm earth-centered cosmos and the Church's later embrace of one creation. Yet the question they asked, could there be other worlds, never really died. You can trace it like a faint thread through medieval scholars, through Giordano Bruno in the 1500s, daring to say that the stars might be suns with their own planets and perhaps their own people. A belief so bold, it helped lead him to the stake in 1600. The whisper of more than one world refused to vanish. Even when silence was safer, modern physics, in its own slow way, came back to this ancient door. When the 20th century cracked open the atom Democritus could only imagine. When physicists found electrons and protons and quarks dancing to hidden rules, something strange appeared. The deeper they looked, the less fixed reality seemed. Instead of solid final pieces, they found waves of probability. Particles that sometimes existed in more than one place until forced to decide. The questions of Democritus returned, but now with experiments attached. In Copenhagen, Bohr and Heisenberg said that probability collapses when observed, an answer both practical and unsatisfying. Then, as you know from the previous quiet hallway, Hugh Everett suggested it might not collapse at all when you stand at this edge. From Greece's open courtyards to Princeton's chalkboards, the long echo becomes clear. Democritus imagined atoms swerving in a void to form endless worlds. Everett imagined wave functions swerving in an abstract space to form endless branches. The language changed, the math deepened, but the instinct feels the same. The known is too thin to hold. The weight of everything that could be. Picture a candle in a dark room. The kind that might have flickered in an ancient study where parchment lay open and Democritus wrote, "The flame seems whole, yet watch closely and you see sparks and glowing fragments breaking free, drifting upward until they vanish. To the eye, there is one flame. To the world beyond, countless tiny departures." This is the image of how old wonder meets new science. The candle we call reality burns in one shape for us. But each instant may throw off hidden sparks, other moments, and other worlds. What makes this reflection powerful is how human it is. Thousands of years apart, the impulse remains the same. To look at the night, at a flame, at the swirl of water in a cup, and feel that what we see cannot be the end. Physics today writes its wonder in numbers and lasers, in quantum tests and cold labs. But at its root sits the same restless question first asked under stars with no names. What if there is more? What if each flicker of chance does not vanish but goes on, unseen? To think this way is not only to dream but to work. Democritus atoms led, centuries later, to chemistry and microscopes in the nuclear age. Everett's many worlds now influence fields like quantum computing, where engineers must decide how to use or guard against superpositions. The bridge between an ancient voice in Abdera and the blinking cryogenic machines of IBM is long. But it is real, so as you hold the idea of a multiverse. No, it is not a sudden invention of modern physics or science fiction. It is an old candle still burning, passed from hand to hand across time, from Democritus sketching atoms, to Epicurus writing of endless worlds, to Bruno whispering stars or suns, to Everett drawing quantum lines on a chalkboard. The flame has changed shape, but the darkness it tries to light remains the same, the unknown vastness. It's just beyond this single world's walls. Hugh Everett III was not the sort of man to be drawn to noise or spectacle. He preferred long hours of calculation, chalk dust on his hands, and a quiet room where he could think without interruption. Born in 1930 in Washington, D.C., he grew up during a time when physics was winning wars and reshaping the world, yet he seemed untouched by grandstanding or fame. He entered Princeton as a graduate student with a clear love for mathematics and the strange promises of quantum mechanics. But even there he walked a solitary road, his mind fixed on a question most considered closed. What really happens when the wave of possibilities in the quantum world is observed? The accepted story, polished and widely taught, came from the Copenhagen school led by Niels Bohr and Werner Heisenberg. It said that before you look, a particle exists as a wave of probabilities. The instant you measure, the wave collapses, leaving one single, definite outcome. Elegant, useful, but to Everett's thinking, not fully honest. He could not accept the idea that something so mysterious and sudden happened merely because a person looked. To him, the universe had no reason to behave one way while unwatched and another way under our gaze. So, in quiet hours through the mid-1950s, he worked on a different vision. One where the wave function, the mathematical object describing all possible states, never collapses at all. Instead, every possibility allowed by the equations continues to exist. When a quantum event has multiple outcomes, the universe itself divides, branching invisibly into separate realities, each carrying on as if it were the only one. To most of his peers, this seemed too heavy a price to pay for elegance. It sounded like a fairy tale written in the language of math. Still, Everett believed the math was clean and necessary. In 1957, at the age of 27, he submitted his PhD thesis under John Archibald Wheeler, a respected and imaginative physicist who saw potential in the work, but also understood how controversial it was. The paper, titled Relative State Formulation of Quantum Mechanics, proposed what we now call the many worlds interpretation. It said the wave function is universal and real, describing not just particles but every observer and every measuring device. When a measurement occurs, the universe doesn't choose one outcome. It simply unfolds into all of them. and each observer experiences just one branch. The reaction was not the breakthrough moment he might have imagined. Though the paper was published in reviews of modern physics, the response ranged from cool dismissal to outright confusion. Niels Bohr, towering in his authority, dismissed it as an unnecessary complication. Richard Feynman, brilliant and skeptical, found it interesting but unconvincing. For many, Everett's view felt impossible to test and philosophically extravagant, a multiverse of unseen worlds born every moment just to avoid a single wave collapse. Better to stay with the familiar Copenhagen story, practical and already powerful in the lab. And so Everett, whose mind had stretched to hold infinite realities, found the door shut almost as soon as he opened it. That rejection left its mark. Though Wheeler encouraged him, the physics community at large offered little interest. Everett grew disenchanted with academia and soon left it behind. Taking a job at the Pentagon, working on complex nuclear strategy problems for the Cold War grim, abstract, and far from the halls of theoretical physics. He did not return to the debates or the conferences. His multiverse idea seemed to fade into footnotes and small, curious references in later textbooks. Friends recalled him as brilliant but withdrawn, sometimes frustrated that what he believed could change physics was left to gather dust. Yet the idea did not vanish completely. A few persistent voices kept it alive, and over time, as experiments in quantum theory deepened, curiosity returned. Physicists like Bryce DeWitt picked up Everett's work in the 1970s and gave it the name Many Worlds Interpretation, a label Everett himself never used. Slowly, the idea found footholds, not as proven truth, but as one possible answer to quantum strangeness. Today, when people speak of parallel universes, of lives splitting off unseen, they echo the quiet work Everett did alone at Princeton while his peers clung to collapse. Imagine him there, young, glasses slightly slipping, standing before a blackboard covered in long lines of wave equations, psi describing everything. No part singled out for collapse. Chalk squeaks. His hand moves with confidence, though the room is empty. Perhaps he knew already that the world might not be ready for what he was writing. Perhaps he believed that truth moves slowly, that an idea can wait decades until others catch up. It is a lonely picture, but also strangely human. A man refusing the easy answer, willing to risk obscurity because the story he had been given felt wrong. The Copenhagen interpretation gave physics a way to talk about measurement and reality. But Everett could not abide its hidden magic trick, the sudden collapse of possibility without cause. He wanted a universe that stayed true to its own rules, no matter who was watching. And so he imagined one vast, unbroken wave splitting endlessly, silent to us but complete. In the years since his death in 1982, Everett's vision has seeped quietly into culture and science alike. Quantum computing, a field unimaginable in his time, works with states that feel closer to his endless branches than to a single collapsed path. Writers, filmmakers, and dreamers have borrowed his vision of infinite lives to tell stories of choice and regret. But behind all the noise and bright images stands the original moment. One man staring at chalkboards full of wave equations, certain that the universe does not end just because we look at it. It begins with a cat that never asked to be famous. In 1935, the Austrian physicist Erwin Schrödinger, frustrated with how strange and unsettled quantum theory had become, imagined a thought experiment that would be simple enough for anyone to picture and strange enough that no one could dismiss the problem. Place a cat in a sealed box, he said, with a small amount of radioactive material, a Geiger counter, a vial of poison, and a mechanism that will break the vial if the counter clicks. If the material decays, the poison is released and the cat dies. If it does not, the cat lives. Quantum physics says the atom exists in a superposition, both decayed and not decayed, until observed. And so, until the box is opened, the cat would seem to be both alive and dead. It was not a joke. Schrödinger meant it as a protest against the Copenhagen interpretation's collapse. How can a cat be both? How can the act of looking decide the fate of a life? Decades later, Hugh Everett's picture of many worlds answered in its quiet, unsettling way. The cat is not both dead and alive in the same single world. Rather, there are two worlds, one where it lives, one where it dies. Each branching from the quantum event of the atom's decay. The box does not hold an impossible creature. It holds two histories waiting to separate the moment the event resolves. Everett's view rescues the cat from paradox, but places the burden on us. Every time a quantum system, with multiple possibilities, evolves, the universe itself divides. These splits are not grand or dramatic. They are too small to feel. That is perhaps the hardest part to hold. How ordinary events, so slight and quiet, could spin off entire realities. A single electron chooses to spin up instead of down. A photon slides through one slit instead of another. And somewhere a line of history veers away. Your body, your senses, your brain continue unaware, because the version of you in each branch remembers only its own path. There is no shudder or break. No one feels half gone. When you toss a coin, physics says before it lands, it is not simply tumbling between heads and tails, but exists as a blur of both. A wave of possibility. The instant it touches the table, reality commits to one, yet in Everett's telling, the other does not vanish. It slides away, unreachably real, carrying with it another you watching another outcome. Imagine slowing the coin down as if time itself could stretch. It rises from your thumb, spins silver in the air, and each glint of light is a branching moment, air molecules it strikes, scatter one way here, another there. The tiny tremors of your muscles shift subtly between versions. In one world it lands heads and laughter fills the room. In another, it lands tails and silence stretches longer. You feel only one because decoherence the deep. Quiet process by which quantum waves lose their ability to interfere. Separates the branches so fully and so fast that no trace remains. It is not that the other world is foggy or less real. It is sealed off, its quantum links unraveled. It's like two books whose pages once touched, but have now been glued shut. Physicists have learned to measure decoherence in controlled experiments. In the 1990s and 2000s, delicate setups trapped ions or fullerene molecules and let them interfere like waves, showing that even large clusters of atoms can sit between possibilities for a heartbeat before interactions with their surroundings force a single outcome to appear. But the scale at which we live is too busy, too warm, too noisy. Decoherence happens so quickly that we feel no fracture. The world seems single and smooth because the splitting finishes before any awareness could notice. And yet, knowing it is happening changes the texture of things. You can sit at a breakfast table and watch sunlight scatter through a glass of water and know that at some quantum level, each photon took many paths, each with its own quiet branch. You can reach for a door handle and know that your atoms, humming with probability, are part of a wave function that once included other choices. We feel whole because our memories are bound to one timeline. But physics does not guarantee that timelines privilege beyond the walls of our perception. This is why the cat matters still. Why the coin matters. Why a single photon's path in a dark lab at Princeton or Vienna matters. They make the unimaginable just barely visible. Schrödinger did not know of Everett's answer, but his cat's imagined heartbeat makes us pause. Everett's many worlds say the pause is real. When the box is opened, there is no single decree from the universe. There is only separation, so fast and final we cannot follow. To live with this thought is not to float lost. It is to feel the richness of the world deepen. A coffee cup trembles slightly as you set it down, and with that tremor, 1,000 quantum events unfold. The air you breathe is filled with unseen particles deciding paths, each choice birthing a fresh sheet of reality. It is easy to think of the multiverse as something vast and unreachable of their galaxies. Other bubbles beyond cosmic horizons, but Everett's idea starts in the smallest. Most fragile places, an electron flipping spin, a photon scattering, a coin in flight. The great infinite is built from things too small to see, so if you close your eyes and imagine the hallway from before, now you might picture not just doors but countless silent threads emerging with each breath and blink. The splits are invisible and painless, happening everywhere, always. You will never feel them, but they fill the unseen structure of what is. In somewhere, in a branch born from the smallest flicker, another you is watching the same coin fall and land the other way. In the quiet years after quantum theory had first shaken the foundations of physics, Albert Einstein found himself deeply uneasy. The equations worked with astonishing accuracy, predicting spectra of light, chemical bonds, and the fine details of atomic behavior, yet they spoke a language that to him felt incomplete. At their core lay probability, a deep and irreducible randomness that said the most we could ever know about a particle was a set of chances, a haze of possible outcomes until the moment of measurement. Einstein, who had spent his career searching for the clear and elegant laws behind light and gravity, bristled at this idea. In a 1926 letter to fellow physicist Max Born, he wrote the now famous line, "God does not play dice with the universe." A simple sentence that carried his lifelong refusal to believe reality could be built on chance alone. To Einstein, physics should describe a world that exists in definite states. Whether or not anyone observes it, his discomfort was not only philosophical. He and two younger colleagues, Boris Podolsky and Nathan Rosen, tried to formalize the trouble in 1935, the paper that would become known by their initials, the EPR paradox. They imagined two particles created together and flying apart. According to quantum mechanics, they remain entangled, their properties linked no matter how far they drift. Measure one particle's spin, and you instantly know the others, even if it's light years away. To Einstein, this spooky action at a distance seemed impossible. No influence should travel faster than light. He believed instead that there must be hidden variables, unknown details that would restore a solid, local reality beneath the probabilities, making the world whole again and protecting it from the dice game quantum theory seemed to play. For decades, that argument remained unresolved. Quantum theory moved forward without worrying too much about the gap. Its predictions kept matching experiment after experiment, and most physicists learned to live with uncertainty. But in the early 1960s, a young Irish physicist named John Bell revisited the EPR puzzle and asked a precise question: if hidden variables do exist, what would they imply about the way measurements on entangled particles should correlate? Bell derived a simple inequality, a kind of boundary for statistics that any local hidden variable theory would have to obey. Quantum mechanics, with its non-local entanglement, predicted violations of this inequality. Suddenly, what had felt like a philosophical quarrel became an experimental challenge. If you could test Bell's inequality and find it broken, you would know that nature itself cannot be explained by any theory of local hidden variables. The quantum dice are real. The first attempts to test this came slowly. Technology in the 1960s and 70s made it hard to prepare clean, entangled pairs and measure them reliably. But by the early 1980s, laboratories had grown quiet and clever enough to try. In Geneva, Alving Specht and his team at the Institut d'Optique set up an experiment firing pairs of entangled photons down separate paths to detectors, whose settings changed so quickly the photons could not, in principle, communicate. Their 1982 results showed a clear violation of Bell's inequality. The correlations were stronger than any local hidden variable model could allow. Quantum theory held. Einstein's hope for hidden order took a deep wound. Across the Atlantic, Stanford and other American labs, similar efforts unfolded. Long optical tables glowed faintly under safety lights. Wires and detectors threaded in patient tangles, red diodes blinking where alignment needed care. Physicists spent nights coaxing fragile particles through polarizers, measuring angles and coincidences with electronics that seemed almost homespun, but were precise enough to reveal nature's secrets. Each run of data piled weight on the same conclusion. The world at its most fundamental level does not behave like a set of hidden gears turning behind the curtain. The randomness is not just ignorance. It is built into the way reality unfolds. Einstein did not live to see these experiments. He died in 1955, still convinced the quantum story was unfinished. But as the decades passed and results accumulated, the Copenhagen camp grew stronger, or at least The idea that quantum mechanics really is non-local and irreducibly strange. Everett's many worlds interpretation, though still a minority view, fit comfortably here. If the wave function never collapses and all outcomes occur, then the randomness we experience is simply which branch we happen to ride. It was no longer a dice game in the sense of chance deciding the universe's path. Instead, all paths exist. And chance is just the view from one thread among countless. Picture one of those early laboratories on a long night. The room hums with cooling fans and the low whir of pumps. A graduate student bends over a table where black optical mounts hold tiny mirrors. Laser light, faintly red to the eye, threads through the air like hair-thin rivers. On a small screen, electronic counts tick upward as entangled photons register their polarizations. There is no grand display, no explosion of color or sound. Just numbers quietly disproving the old hope that the world hides secret variables to keep it tidy. Outside, the Geneva night presses against tall windows. At Stanford, the cool California air rustles eucalyptus leaves beyond the physics building. In these modest rooms, the dice are thrown and found real. For those who love certainty, it is a hard truth. The universe, as far as these tests can tell, is not clockwork underneath. It does not wait for us with fixed answers. Instead, it swells with probability, in each event a photon choosing a path. A particle's spin aligning one way or another is a place where reality itself can unfold unpredictably. To Einstein, that meant incompleteness. To later physicists, it meant wonder. A world larger and stranger than even his great mind could accept. And for the idea of many worlds, it opened a door. If the dice cannot be taken from the table, perhaps every throw, every outcome, is simply taken into its own branch of existence, leaving us here with our single sum of the roll, while somewhere unseen, another version of us watches the dice fall differently. There is a moment, sometimes so small you would never notice it, when a choice is made and a life slides one way instead of another. It might be a word said or unsaid, a step taken, a phone answered or ignored.
Right.
And to you it feels like nothing more than the ordinary turning of the day. Yet if Hugh Everett's picture of reality is right, that quiet instant is not just a turn, but a split. Somewhere in the invisible machinery of quantum events too delicate for any sense to feel, a version of you followed the other road. The universe did not erase what might have been. It let it live, branching into a future you will never see, but that is as real and intricate as the one beneath your feet. This idea can seem like mathematics, until you let it come close. Until you picture ordinary things, you are invited to a gathering, and at the last minute you decide to stay home. In one world, you settle into your couch with a book and silence, while in another, you walk out the door. And the night unfolds with faces and conversations that will weave themselves into that other youth future. You receive a job offer and say yes, but somewhere else you politely decline, and the rhythm of your days changes forever. You stand in a train station and catch the early departure. In another branch, you miss it by seconds, and the delay changes who you meet and where you land. Each choice feels small, but each is tied to endless threads of quantum possibility. The world you feel is whole and solid is just one of those threads. There is a strange kind of weight in imagining this.
Yes.
Though it is not a heavy weight so much as a quiet deepening. It is one thing to speak of particles splitting paths, its electrons spinning this way and that, but another to imagine all the selves you could be moving through their separate days. The science insists you cannot reach across or visit. The split is absolute, and the branches decompose so quickly that no trace of the other survives. Yet the thought that there are silent twins versions of you waking up to different light, saying yes where you said no, brings a kind of humility. It shows how delicate each moment really is, how the solid life you know is only one story among countless possible ones. To help the mind see it, imagine a single mirror falling and striking the floor. At first, there is one reflection, whole and clear, and then in a single instant, the glass bursts apart. Each shard still holds a face, a room, a slant of light, but now there are dozens, hundreds, all true and all separate. You remain standing in one piece of the reflection, while all the others scatter beyond your reach. That is how physicists describe the multiverse, not as theory, but as natural unfolding, not a conscious splitting, not a door you walk through, but a shattering that happens every time chance is present at the quantum level. The emotional impact of this can cut both ways. Some find comfort in it, the idea that nothing is truly lost, that somewhere every path is taken and no door is left forever closed. The regret that lingers over a missed opportunity might soften if you imagine. Another, you stepping forward where you hesitated. Others find it unsettling, the thought of infinite lives unspooling beyond their control. Each version of themselves both familiar and unreachable. It can feel like standing before a vast sea of shadows and knowing you can touch none of them. Yet, even in its strangeness, there is something grounding. The science does not demand that you track or count these selves. You will always be whole within your branch, your memories intact, your body unbroken. The person who stayed home last night will not wake up tomorrow with a ghost of the party in their mind. The person who went will not sense the quiet evening you had. Decoherence, that rapid uncoupling of quantum worlds, is complete and merciful. Each path becomes sealed to its own history, and so life remains livable, even if it is on a deeper level. Only one among countless. Physicists have debated whether this picture is truly necessary, whether it is better to accept randomness and collapse instead of multiplying worlds. But as quantum theory keeps proving how stubbornly non-local and probabilistic nature is, many find Everett's unbroken wave compelling. It does not ask the universe to choose or destroy possibilities. It lets them all persist. In this way, the infinite is not a special feature bolted on, but simply what happens when you let the equations play out honestly. If you stand quietly for a moment and consider your own past, the job you did or didn't take, the call you answered, the person you kissed or let pass by, the sense that life is narrow may soften. Each path you remember was a gate to countless others, and though you cannot see them, they exist in the silent geometry of the quantum world. This is not an excuse to stop caring. If anything, it underscores how precious the road you are on is, how full of consequences every ordinary moment becomes when you realize it. It's one of an endless fan of choices, so when you picture yourself, try sometimes to see beyond the single reflection. Somewhere the version of you who studied another subject sits at a desk you have never seen. Somewhere, the you who left town years ago wakes to different weather. Somewhere the coin landed the other way. These other lives are closed to you, but their presence whispers of a universe far larger than the one mapped by streets and clocks. And within that vastness, the life you inhabit now is both impossibly small and astonishingly rare, one fragile shard of mirror catching the light just as it falls. When Stephen Hawking stood before an audience in the early 1970s and argued that black holes are not entirely black, the room felt a little unsteady. Until then, the picture had been brutal but simple. A black hole was a one-way door, a region of space-time where gravity became so overwhelming that nothing, not even light, could escape once it crossed the event horizon. Matter fell in, signals vanished, and the details of what had been swallowed seemed lost forever. But Hawking, working with the uneasy marriage of general relativity and quantum theory, found that the edges of a black hole were not silent. Tiny quantum fluctuations near the horizon could produce pairs of particles. One falls in, the other escapes, and to an observer far away, it looks as though the black hole itself is glowing faintly. This Hawking radiation, as it came to be known, meant black holes could evaporate over immense timescales, slowly losing mass and eventually disappearing into nothing but light. The beauty of the idea carried a hidden wound. If a black hole can vanish, what happens to the information about what fell inside? In classical physics, information about the arrangement of matter is never truly destroyed. Even if something burns, the details are scrambled, but in principle, recoverable. Yet Hawking's radiation seemed to carry no imprint of the things consumed, no trace of stars, planets, or unlucky spacecraft. When the black hole finally faded, the information would be gone forever. This became the black hole information paradox, a rift between the quantum world, where information must be conserved, and the curved spacetime of Einstein, where destruction seemed possible. For decades, the paradox haunted theoretical physics, a silent dare from the edge of the abyss. Some began to wonder if the answer might reach beyond the universe we know. If information cannot vanish but a black hole appears to erase it, perhaps the lost details slip somewhere else into another branch of the quantum wave, another part of the multiverse. Hawking himself toyed with this, suggesting at times that information might leak out subtly, entangled with radiation or perhaps stored on the event horizon itself like bits on a cosmic hard drive. Others imagined more radical escapes. What falls into a black hole could butt off into a new universe entirely. Baby cosmos pinched off from our own, where the swallowed data lives on in another form. These were speculations at the edge of known science. But they shared a quiet theme with Everett's many worlds. Reality may never truly discard possibilities, only root them somewhere we cannot follow. By the 2010s, the paradox had evolved into fresh puzzles. In 2012, a group of physicists proposed what came to be called the firewall hypothesis. According to their calculations, if information is preserved and quantum mechanics holds fully at the horizon, then the smooth, gentle boundary that general relativity predicted would be impossible. Instead, there would be a searing firewall, a band of violent energy obliterating anything that tries to cross. This clashed with the long-standing belief that an astronaut falling into a black hole might not even notice the horizon until tidal forces tore them apart deeper inside. The firewall debate became one of the sharpest frontiers of modern physics, a sign that black holes still hide secrets about space, time, and perhaps other realities. If the horizon is not smooth, if information bounces or burns or tunnels, then something about our single universe picture is incomplete. While theory wrestled with paradox, observation took a slow and patient leap. In April 2019, the Event Horizon Telescope, a global array of radio observatories working together to mimic a planet-sized dish, released the first direct image of a black hole's shadow. It was the supermassive object at the heart of galaxy M87. 55 million light-years away, a dark disk encircled by a glowing ring of hot plasma. The picture, grainy and yet profoundly moving, showed that we could finally glimpse the edge of no return. For many watching that day, the image was not just a technical triumph, but an emotional one, proof that the deep hum of space could be touched by human effort, that the invisible could be seen. And in its quiet way, it also reminded us of the puzzles waiting there. The light we saw came from matter still outside the horizon. But beyond that glowing edge lay the place where questions about information, reality, and other worlds deepen. Imagine standing near that monstrous object, not close enough to die, but close enough to feel the slow churn of space-time. Around you, the accretion disk blazes, a whirl of gas and dust, heated to millions of degrees. Circling at nearly the speed of light, glowing red and gold and white in the darkness, there is no sound yet. In your mind, you hear a low, endless hum, as though space itself is straining. Each fragment of matter plunging toward the horizon carries with it a story what it once was, where it came from, and yet once it crosses that line, the story seems to stop for us. Theories argue about whether those tales are really lost, whether they hide in faint ripples of Hawking radiation, whether they are etched somehow on the surface like a cosmic ledger, or whether, as some dare to imagine, they pour into newborn realities beyond our reach. For the multiverse, black holes remain tantalizing. They are places where our best descriptions of reality clash most violently. Einstein's smooth geometry meets quantum theory's insistence on information and probability, and neither yields easily. If anywhere hints of other outcomes, other branches might slip through, it would be here, where space-time itself folds in on its own rules. And though no experiment yet can tell us if a black hole opens a doorway to other worlds, every new image, every sharper test of radiation and gravity, pushes us closer to knowing how complete or incomplete our single universe really is. In the end, the paradox is still alive, though softer than when Hawking first named it. Many physicists now suspect information is not destroyed, that quantum laws remain intact, but exactly how they survive the crushing gravity of a black hole is still veiled. For those willing to wonder, that veil feels like a whisper, perhaps of parallel outcomes hidden in the dark, perhaps of other halls branching off the one we walk. What is certain is that black holes, once imagined as simple graves, have become mirrors turned toward the deepest structure of reality. Places where we test whether the universe ever really lets go of what it has been. In the late 1970s, a young American physicist named Alan Guth sat at his desk at Stanford wrestling with an old puzzle that had bothered cosmologists for years. Why does the universe look so smooth and uniform on the largest scales when, according to the Big Bang, it should have been chaotic and uneven? He was trying to explain a simple but haunting observation, that no matter where you look in the sky, the cosmic microwave background, the faint afterglow of the early universe, has almost exactly the same temperature. It should not. Distant regions were too far apart at the start to ever have shared information or balance their heat. Guth's answer, when it came, would change how we imagine everything. He proposed that in the first tiny fraction of a second after the Big Bang, space itself underwent an unbelievable expansion. An inflation so fast and so violent that it smoothed out wrinkles like dough rolled under infinite pressure. Inflation, as Guth named it in 1980, did more than solve the smoothness puzzle. It opened a door far stranger, because if space can inflate once, driven by some high-energy field pushing outward, it might not have stopped everywhere. Inflation could be eternal, bubbling and blossoming forever. In Guth's picture, our entire observable cosmos, the galaxies, the voids, the light we see is just one bubble among countless others, each formed when a pocket of inflating space slowed and cooled enough for matter and stars to appear. Beyond our horizon, unreachable and unseen, space might still be inflating, spawning other universes with different properties, different physics, different fates. Imagine it. We sit on a small planet, circling an ordinary star, inside a galaxy among hundreds of billions. Yet all of that is just one froth bubble on an endless cosmic sea. Each bubble is its own universe, with its own story of birth and expansion. Some may have more dimensions, some fewer. Some may collapse quickly, some expand forever. Some might host matter but no stars, or stars but no chemistry to build life. Our bubble cooled to the familiar laws we know, electrons with their charge, protons with their mass. Gravity weak but present, but there is no reason nature must choose the same recipe everywhere. The physics of inflation suggests the rules can reset with each newborn cosmos. If you step far enough back in your imagination, you can picture Earth shrinking away under clouds and blue seas, the continents fading, the solar system slipping to a point of light. Keep pulling back, and the Milky Way becomes a hazy swirl, then vanishes among filaments of galaxies stretching across darkness. Pull back further, beyond what any telescope has mapped, and you reach the edge of our visible universe, a pale shell marked by the cosmic microwave background. A faint bath of microwaves left from when everything was hot plasma about 380,000 years after the Big Bang. That glow is the oldest light we can see, but it is not a wall. It is just the limit of what light has had time to reach us. Past that horizon, inflation says, the sea goes on. More space, still expanding, still sprouting bubbles like ours, each invisible to the others because their light will never catch up. Physicists call this the multiverse, born of eternal inflation. It is not fantasy, but a natural outcome if the inflationary field, whatever it is, decays in patches rather than all at once. The mathematics says expansion outruns its own stopping, leaving behind islands of calm where big bangs ignite while the surrounding ocean keeps stretching faster than light. Those islands are universes, each causally cut off from the others, each with its own timeline and its own sky. Our cosmic microwave background, measured first accidentally by Arno Penzias and Robert Wilson in 1964, as a mysterious hiss in their radio antenna, may be just one patch of a larger quilt. Some cosmologists even search that faint glow for scars, for places where another bubble might have brushed against ours long ago. leaving a cold or hot spot as a fingerprint of contact. So far, the evidence is murky. The universe does not easily give up its oldest secrets, yet the vision persists because it fits so elegantly. Inflation explains why the cosmos looks flat and smooth, why galaxies are distributed the way they are, why the cosmic background's temperature varies so slightly, 1 part in 100,000. And if inflation is true, eternal inflation follows almost inevitably. The same process that birthed us does not know how to stop. It simply keeps going somewhere else. Goethe himself has said, "It is like soap suds, blowing forever, each bubble expanding to a size beyond imagination." While more appear unending lie, there is something both terrifying and beautiful in this picture. Terrifying because it makes our known universe, already vast beyond comprehension, seem like a single droplet in an endless ocean. Beautiful because it suggests that creation is not an event but a process still alive, still happening in the dark beyond our sight. Every second, perhaps, new spaces blooming, new laws are being written, and new stars may one day rise in universes we will never touch. Stand for a moment in your mind's eye and look up at the night sky. The microwave background, though invisible to your eyes, bathes everything, a whisper from 13.8 billion years ago, cool now but once fierce and blinding. That faint afterglow might not only mark the edge of what we can see, but hint at countless other skies, other cosmic dawns beyond it. If you could travel faster than light and cross the gulf, you might break through to a universe where the constants are not ours, where atoms do not bind the way they do here, where life may be impossible or unrecognizable, but we are sealed to our bubble, its horizon forever racing away. And yet knowing this changes how the night feels. The stars overhead are no longer lonely. They are part of an unending, unseen archipelago of creation. Goethe's idea, born of trying to solve a simple puzzle about smoothness, has turned into one of the grandest possibilities physics has ever dared to hold. The sea of bubbles might remain forever beyond our reach, but it is enough to know that we drift on one of them, fragile, improbable, and yet luminous in a way we can finally imagine. If not touch, when Max Tegmark was a young student studying physics in Sweden and later at MIT, he found himself haunted by a question that seemed almost childlike in its simplicity, but carried a weight that could topple whole views of reality. What is the universe really made of? Not just the atoms and forces, not just the fields and particles, but at the deepest level, what is the fabric? The more he learned, the more one answer kept shimmering through every corner of physics, mathematics. Gravity obeyed equations that Einstein had written with curved tensors. Light moved as James Clerk Maxwell once described in differential forms. Quantum mechanics danced through Schrödinger's wave function and Dirac's elegant symbols. Again and again, the wild variety of nature could be captured and predicted by abstract symbols on a page. At first, it might seem obvious. Of course, physics uses math, but to Tegmark it was not enough to say math was a language. He began to suspect math was the thing itself. From that suspicion grew what he would later call the mathematical universe hypothesis. If the laws of our cosmos can be perfectly described by mathematics, and if mathematics, as a structure, exists beyond any single universe, then perhaps all mathematically possible structures exist as their own physical realities. In other words, every equation that can define a consistent world is not just an idle pattern in a textbook, but an actual universe with space, time, and observers who can live and wonder within it. Our cosmos would not be special, only one of countless self-consistent solutions to the rules of logic. As Tegmark sometimes puts it, mathematical existence and physical existence may be the same thing. To hold this idea, imagine stripping the world down until only the patterns remain. Take away the colors and textures of a tree, the scent of its sap, the play of sunlight through its leaves, and you are left with relationships, angles between branches, rates of growth, the spiral of leaves along a stem following the Fibonacci sequence. Remove the weight and warmth of the earth itself, and gravity remains as a curvature of space-time described by Einstein's field equations. Remove the hum of electrons, and you have the Schrödinger equation humming in their place. If all the richness of the world can be rebuilt from mathematics, Tegmark asks, then why think of math as mere description? Perhaps it is the blueprint and the building at once. His proposal first took shape in the 1990s, matured in his 2014 book, Our Mathematical Universe, where he described a level 4 multiverse, a step beyond. The many worlds of quantum physics, or the bubble universes of inflation. In level 4, every coherent mathematical structure is real. Not just the worlds born from quantum splits, not just the bubbles spawned by eternal inflation, but any internally consistent set of equations becomes a universe. Somewhere, there are worlds of different dimensionalities. Worlds with alternate physics, worlds where logic itself might take forms that would baffle human minds but still remain self-consistent. It is an unsettling but strangely beautiful view. If true, it means reality is not built from particles or strings, but from math itself. Shapes and relationships that do not depend on our minds to exist. It would also mean that our own universe, with its specific constants and laws, is simply one solution among many. We do not live in the only possible cosmos. We live in a cosmos that happens to support observers like us, able to write down its equations and notice the pattern. In that sense, physics becomes not the search for a single ultimate theory, but the search for the particular corner of the mathematical landscape that we inhabit. To picture it, close your eyes and imagine symbols floating in dark space, Greek letters, integral signs, matrices. Now imagine them turning slowly, interlocking, giving rise to forms. A grid warps and becomes the geometry of space-time. A wave equation ripples until it births the quantum fields of electrons and quarks. The fine structure constant emerges like a faint thread stitching atoms together. Keep going, and the abstractions condense into light, matter, oceans, faces. Somewhere inside one particular equation, Earth takes shape. And you stand looking back at the numbers that made you possible. This is the dream Tegmark describes. That mathematics is not just a map of the territory, but the territory itself. There are critics, of course, and the debates run deep. Some argue that mathematics is a human invention, a tool shaped by brains evolved to count and measure. Others counter that mathematical truths seem discovered rather than invented, their consistency beyond culture or biology. Tegmark's claim goes further than most physicists are willing to travel because it blurs the line between physical and abstract existence. It says the Platonic world of forms is not separate from the world of stars and atoms, but identical to it. There is no need to ask why the universe is mathematical. It simply is mathematics. Yet even those who find it too daring admit the odd effectiveness of math is a mystery worth exploring. Eugene Wigner once wrote an essay in 1960 called The Unreasonable Effectiveness of Mathematics. In the natural sciences, marveling that so many seemingly abstract constructs end up describing reality with uncanny accuracy. Maxwell's equations for electromagnetism, derived from elegant reasoning about fields, turned out to describe not only wires and sparks, but the invisible waves that would one day carry radio, Wi-Fi, and signals across the planet. Einstein's equations of relativity, shaped from thought experiments about falling elevators and light beams, predicted black holes and the expansion of space decades before telescopes confirmed them. Again and again, math seems to know the world before the world confesses its details. Tegmark's vision, if you let it sink in, reshapes how you think about existence. It says that somewhere in the vast, cold library of possible equations are universes of every kind. Some barren, some vibrant, some unknowable to us, but still real. Our own lives are lines of computation playing out inside one solution. The great multiverse is not merely a sprawl of physical bubbles or quantum branches, but the full space of all math itself. Infinite and silent, you do not need to accept it to feel its pull. Simply imagine that behind everything, behind the sunlit hills, behind your own heartbeat, is an invisible lattice of relationships that would hold even if no mind observed them. And imagine that lattice as one among endless others, each giving rise to worlds that will never meet ours. It is a strange comfort. The idea that we are part of something so vast, a pattern that does not end where our senses stop. A story written in symbols older than time. Still unfolding line by line, there are moments when the night sky seems utterly still. Endless and clean, yet the deeper we have learned to look, the more signs appear that our universe might have been touched, however faintly, by things beyond its edge. In the early 2000s, astronomers studying the oldest light we can see, the cosmic microwave background, noticed something unusual. This light, a soft bath of microwaves stretched thin by nearly 13.8 billion years of expansion, fills the sky evenly with tiny ripples that reflect the first seeds of galaxies. But among those ripples, there is one patch, larger and stranger than the rest. A region where the glow is unexpectedly cool and smooth. It is called the cold spot, and it sits deep in the southern hemisphere of the sky, near the constellation Eridanus. At first it was just a curiosity, a statistical hiccup perhaps. But over time it has come to symbolize something wilder. Maybe, just maybe, our universe brushed against another. The idea did not spring out of nowhere. Cosmologists had long known that if the universe is one bubble among many, as Alan Guth's inflation theory suggests, then collisions between young universes might leave scars. When two inflating regions meet, the violent expansion could imprint distortions in the fabric of space. Faint fingerprints preserved in the microwave background, like bruises on an otherwise smooth skin. But for years, these were only abstract predictions, until instruments became sharp enough to test them. The Wilkinson Microwave Anisotropy Probe, WMAP, launched by NASA in 2001, gave us the first truly detailed full sky maps of the cosmic background. It scanned the heavens for 9 years, measuring temperature differences down to millionths of a degree. Its data gave us a universe astonishingly flat and uniform. Yet in 2004, a team led by Kate Land and Joe Maguayo pointed to that cold patch in Eridanus. Too wide, too deep, they said, to fit easily with random quantum fluctuations from the early cosmos. They did not claim a multiverse outright. There are other possible explanations. It's like an immense underdensity of galaxies known as a supervoid. But the whispers began. If our universe ever grazed another bubble in its infancy, long before stars and atoms, the wound might look just like this. When WMAP retired, the European Space Agency's Planck satellite took its place. Launched in 2009 and scanning until 2013 with even finer resolution and sensitivity, Planck's maps confirmed the cold spot was real. It was not an artifact of instruments or data errors. Yet the debate only deepened. Some cosmologists argued the feature could still be an extreme but natural fluctuation. Others thought the supervoid explanation plausible but incomplete. The void measured along that line of sight is deep, but perhaps not deep enough to create so cold a mark. A smaller group dared to say it fits well with certain models of cosmic patch bubble collisions. Picture the work that went into these maps. Satellites drifting far beyond the radio noise of Earth. Their detectors chilled to fractions of a degree above absolute zero, sweeping the sky again and again. Data streamed home and was turned into false color charts, red and yellow for slightly warmer patches, blue for slightly cooler, the whole universe reduced to subtle swirls of temperature differences measured in microkelvins. Most of the map is gorgeous but bland, a cosmic baby picture with patterns that inflation theory predicts. And then there is that odd bruise, not bright, not glaring, but stubbornly there. It is tempting to jump to wonder. A young universe, ours, still inflating, slams softly against another expanding region. The meeting halts expansion locally, leaves a circular imprint, and then both move on. Forever parted by faster-than-light growth. Billions of years later, tiny creatures in one of those universes build machines and discover the faint scar. The story feels mythic, and yet is quietly allowed by the math. But science moves slowly and demands caution. Many researchers insist the evidence is not enough. One strange region cannot yet prove anything beyond cosmic variance. The fact that randomness sometimes produces oddities. Others suggest our understanding of large-scale structure, like giant voids and filaments of galaxies, is still incomplete. Yet even cautious voices admit the cold spot is among the most puzzling anomalies in precision cosmology, a clue that will not go away. For those willing to wonder, the visual itself is haunting. Imagine floating far beyond Earth, beyond the solar system, beyond even the Milky Way, till galaxies blur to fog and the edge of the visible universe looms. The microwave background wraps around like an ancient shell, glowing faint and soft, and there, in the darkness near Eridanus, is a patch dimmer and smoother than it should be. A bruise left by something we cannot name. These are not the only hints. Smaller anomalies, alignments of temperature patterns nicknamed the axis of evil, hemispherical asymmetries. Puzzling low quadrupole power have stirred similar questions, though none rise alone to certainty. They may be flukes, they may signal physics we do not yet know. Or, if the grander visions are true, they could be echo shadows of universes we will never meet. What matters is that our tools have reached a place where such questions are no longer only philosophy. Satellites like WMAP and Planck, and soon new missions such as Lightbearer and ground arrays like the Simons Observatory, aim to peel back the cosmic microwave background with greater precision still. They look for patterns in polarization, for telltale ring shapes or gradients that might whisper of an ancient collision. Meanwhile, in offices and observatories, scientists scroll through sky maps that look almost empty yet hold the oldest messages we have. They debate probability and cosmic variance. But in quiet moments, some surely let themselves feel the wonder. Perhaps our bubble once touched another, long before there were humans or stars, and we are the faint aftershock. A scar no deeper than a whisper, but enough to hint that we are not alone. And even if future data proves the cold spot a trick of chance or void, the exercise itself reshapes how we see the sky, not as a final, closed room, but as one wall of a larger house, marked faintly where it once pressed against something beyond, in the small hours of the night. When the noise of the day has fallen away and the house seems to hold its breath, the mind begins to wander across boundaries it cannot name. Sleep comes like a tide, it's pulling you under until familiar walls dissolve and new landscapes rise, cities you have never walked but somehow know, voices you have never heard yet recognize with warmth or dread, choices you have not made yet feel as though you once lived. Dreams have always been our first, most intimate contact with the idea of other lives. Long before physicists debated quantum mechanics, long before Hugh Everett wrote about branching worlds, human beings closed their eyes and slipped into stories where time folds and identity blurs. In that way, dreams could be thought of as the oldest multiverse. It's private and unmeasured, but endlessly convincing. Psychologists have spent decades trying to chart this night country. They know that during rapid eye movement sleep, when the brain is as electrically active as it is when awake, memories and emotions scatter and recombine. Experiences from the day, fragments of long-buried moments. Fears and desires all drift together and build scenes as vivid as waking life but unbound by its rules. Yet there is something in the texture of dreaming that goes beyond mere recycling. Many people report stepping into lives they do not remember living, working jobs they never trained for, speaking languages they have never studied, meeting people they know but could not name while awake. These details vanish at dawn but leave behind a residue, a feeling of having brushed against another self. It is here that the quiet language of physics sometimes slips into ordinary talk. We wake from a dream where we were older, or where we chose differently, and say it felt like a glimpse of another life. Of course, there is no proof. The brain is fully capable of invention. But the power of these moments is not about evidence. It's about the deep craving to believe that the paths not taken are somehow still alive. Evolution may have given us this craving as a way to imagine, to rehearse, to plan for futures by exploring them safely in sleep. Yet when paired with the modern knowledge that quantum events do branch reality, the old habit takes on new resonance. Perhaps some wonder quietly, these are not just inventions but faint echoes of the other roads our atoms might have followed. Déjà vu intensifies that wonder. It is a fleeting, slippery sensation, a moment when present experience floods with an uncanny familiarity, as though you have stood in this hallway or heard this conversation before in some other life. Neurologists explain it as a glitch in memory circuits, a misfire between short-term and long-term recognition. Still, the experience itself is deeply convincing. For an instant, you feel as though two versions of yourself have overlapped, Cultures across centuries have given it mystical readings, glimpses of fate, echoes of past lives, hints of cosmic recurrence. In the age of quantum speculation, it has been adopted again. Maybe, just maybe, this is a brush with another branch of reality, close enough to touch for a breath before vanishing. There's no experiment that proves any of this. Neuroscience remains clear that dreams and déjà vu arise from the brain's own intricate but local processes. Yet the persistence of these feelings speaks to something in us that wants the world to be larger than the single thread we can hold. We are built to imagine, and the knowledge of a multiverse has given our oldest nighttime intuitions a new framework. Where once dreams were omens or visions from gods, now they can be framed as a kind of psychological quantum travel, journeys across what might have been. Picture a quiet sleeping room, shutters drawn against the night. On a small table, a lantern burns low, its flame flickering softly against the walls. Inside, a person sleeps deeply, their breathing even, their eyes moving under closed lids as the dream sweeps them away. In one dream, they are standing at a train platform that does not exist here but feels known. In another, they are speaking to a friend who died long ago, but is alive and laughing. Outside the walls, the dark is heavy and still, but within the mind, entire worlds bloom and fade, each as vivid as waking. This is the oldest laboratory humans have known. The one every child enters without instruction. Even when we are awake, the urge to peer sideways persists. We imagine alternate outcomes of our choices, sometimes painfully, sometimes with hope. Regret itself is a kind of multiverse longing, the wish to visit the world where you said yes, or stayed, or turned in time. Art and story feed this desire. Books let us step into other lives. Cinema shows us worlds where the coin fell differently. Science fiction thrives because it joins the rigorous with the impossible, turning Everett's mathematics into roads we can travel with our hearts. Scientists know these inner voyages do not prove parallel universes, yet many quietly admit the kinship. Physics says each quantum event can branch reality. Psychology shows the brain is built to imagine branching anyway. Perhaps these two truths meet not in evidence but in metaphor, a human way of living with the ungraspable scale of possibility. Our minds rehearse the multiverse long before instruments confirm or deny it. There is a soft comfort in this. We are sealed to one life, but not to one imagination. Each night we travel, rebuild, and try on other fates. Each sudden jolt of familiarity during the day reminds us that our brains are forever mapping, comparing, searching for hidden continuities, whether or not any of it touches real alternate worlds. It shows the same hunger that drives the hardest science, a refusal to believe reality stops at what we see, so we let the lantern burn through the night and surrender to sleep, trusting the ancient, patient machinery of dreaming. We drift through cities that never were, speak to loved ones lost, make different choices, and feel their weight. Then morning comes and we wake, carrying only fragments, but also a subtle sense that life is deeper than the narrow track we remember. The multiverse may be unreachable, yet in the theater of the mind we have always been slipping between worlds. Searching for some echo of the infinite paths our waking selves will never walk. There is a quiet rebellion happening at the smallest scales of reality, a kind of gentle defiance of the rules we think should hold. In the classical world we know, the world of walls and locks and solid doors, if something lacks the energy to climb over a barrier, stays trapped. A ball too weak to roll over, a hill rolls back. A person facing a closed door without a key stays outside. But the quantum world is not so obedient. Particles, wrapped in their wave-like nature, do not sit politely and wait for enough energy to move. They blur, they spread. They have a small, but real chance of appearing on the other side of a barrier that should have stopped them. This phenomenon, discovered in the early decades of quantum theory, is called tunneling, and it is as strange as it sounds, a subatomic trespass that would seem impossible if we only trusted. Everyday intuition. The first hints came in the 1920s and 1930s, when physicists noticed certain nuclear processes that classical physics could not explain. Alpha particles, for instance, escape from the heavy nuclei of elements like uranium and thorium, even though By the known laws, they should be forever imprisoned by the intense nuclear force holding them in. George Gamow, a young Russian theorist, showed that quantum mechanics allowed the particle's wave function, the ghostly spread of possible positions, to leak through the nuclear barrier. The alpha particle could appear outside, not because it climbed over, but because it blurred through. The math fit beautifully, and the idea stuck, though it felt like a violation of common sense. Over the following decades, tunneling proved to be more than a nuclear curiosity. It began to show up everywhere, an invisible trick of nature that powers technologies and even stars. In the sun, for example, hydrogen nuclei must fuse to create helium and release the light that warms Earth. Yet the protons inside our star do not have enough energy, given the sun's temperature, to overcome their mutual electric repulsion and collide. Classical physics would say fusion should be rare and the sun too dim. But quantum tunneling allows the protons to sneak through their energy barrier and fuse far more readily, making the sun shine and life possible. Without tunneling, our universe would be cold and dark. Scientists learned to harness this strange escape. By the mid-20th century, engineers were building devices like tunnel diodes and Josephson junctions, thin barriers between superconductors where electron pairs can tunnel and produce precise quantum effects. These devices became the beating hearts of extremely sensitive instruments, including some of the best detectors of magnetic fields and tiny voltages. Josephson junctions today are part of the circuitry in quantum computers, machines that rely on delicate quantum states to compute in ways no classical system can, inside labs at IBM, Google, and universities around the world. Rows of quantum processors sit housed in gleaming metal canisters, chilled to temperatures within a fraction of a degree above absolute zero. Peer inside, and you would see the strange blue glow of cryogenic shielding and the elegant, almost organic tangle of cables feeding signals to qubits, the quantum bits that can hold 0 and 1 at once until observed. These qubits, whether based on superconducting loops or trapped ions, are masters of the tunneling world. They exploit the fact that quantum states can seep across what looks like a barrier, letting information process in superposed ways and perform calculations that would take classical computers ages. The fragile dance of tunneling electrons in Josephson junctions allows the control pulses that make qubits flip, hold, and entangle. It is easy to think of tunneling as a mere curiosity of machines, but at its heart it is another reminder that reality is not the hard surface it appears to be. Every second in your body, electrons tunnel between molecules, process critical in biology, including the reactions that let mitochondria power your cells. In semiconductors, tunneling shapes the leakage currents that define how small and efficient transistors can become, indirectly controlling the march of computing technology that has changed society. Each small act of a particle slipping where it should not reverberates outward in ways that shape timelines far larger than the particle itself. For the vision of the multiverse, tunneling is not just a technical note, but a symbol. When a particle's wave leaks and resolves on the far side of a barrier, quantum theory says all outcomes coexist until dicoherence picks one. Some branches contain a particle that passed through. Others contain a particle that stayed behind. We experience the outcome where the trespass succeeded or failed, but the other possibilities remain alive elsewhere. In this sense, the smallest act of defiance against classical confinement is also a tiny branching of worlds. Consider the image. A particle confronted with a hill it cannot climb, its wave function swelling against the barrier, faintly but steadily penetrating, until on the far side, a new reality emerges where it arrived. Physicists have measured this in exquisite experiments, trapping electrons and watching them tunnel through potential walls. Timing the passage so brief, it seems instantaneous. The numbers match the strange predictions of quantum theory exactly. The effect is as real as gravity, even if it defies human logic. The great blue machines of IBM and other quantum labs are monuments to this truth. Inside them, qubits are like coins spinning on edges we cannot see, probabilities bleeding through boundaries to make new computational landscapes. Their success shows that the bizarre is reliable. Tunneling is not a glitch, but a fundamental rhythm of nature. If you let the thought travel outward, it becomes almost poetic, a universe that allows particles to refuse confinement. To pass through what seems impossible may allow reality itself to branch and rebranch. The small trespasses we measure in the lab echo the deeper claim that no barrier is absolute, but that what we call final walls might only be shadows cast by our limited sense. Each ghost-like leap at the quantum level is part of the story of a universe that does not settle for one outcome. That always holds more possibility than the surface suggests, so the next time you see the frosted, cathedral-like silhouette of a quantum computer or read about an experiment, timing the passage of a single electron through an impossible barrier, remember what is really happening. The ordinary rules breaking softly, the door giving way without opening. The future widening at a scale so small, we will never feel it, but so constant we owe sunlight and life to its quiet trespass. In the mid-1990s, a quiet but far-reaching idea began to take hold among theoretical physicists. One that grew from long battles over black holes and their secrets. It started with the same paradox that had troubled Stephen Hawking. If black holes eventually evaporate through Hawking radiation, what happens to the information about what fell in? The laws of quantum mechanics do not allow information to vanish. Yet general relativity seemed to insist that once matter crossed the event horizon, its details were gone forever. Among the physicists wrestling with this conflict was Leonard Susskind, a restless thinker who had spent years pushing string theory forward. He and others, including Gerard T. Hooft, began to suspect the answer was stranger than anyone had guessed. That perhaps the three-dimensional universe we know is not as deep as it appears. Perhaps reality can be fully described by information stored on a distant surface. It's like a vast cosmic skin. This was the birth of what is now called the holographic principle. A hologram, the kind you might have seen on an old credit card or a piece of art, stores a three-dimensional image on a two-dimensional surface. Light striking the hologram carries the full depth of the picture, yet the data lives on the flat plate. Susskind and T. Hooft imagined something similar for the universe itself. The entire contents of a volume of space could be described by data encoded on its boundary. The information about everything that falls into a black hole might be preserved not inside, where it seems lost, but on the horizon itself, smeared across the surface at a density of about 1 bit per Planck area. Unimaginably fine, but enough to account for all the swallowed complexity at first. This was aimed narrowly at the black hole paradox, but like many bold ideas, it grew until it touched almost everything. If the physics of black holes demands that their interiors are fully described by their horizons, and if the same quantum gravity that governs black holes also governs the universe, then maybe our entire cosmos is holographic. The space we move through, the stars and planets, and even our bodies, could be the unfolding of information written on some faraway boundary we will never see. Our three-dimensional experience might be a projection of a deeper two-dimensional structure. In a sense, we could be shadows of mathematics so pure and simple that it needs one dimension less than we do. This vision became sharper with the work of Juan Maldacena in 1997, who proposed the ADS-CFT correspondence, a powerful realization of holography that linked a theory of gravity in a curved bulk. Space, with a quantum field theory, living on its boundary. His example used anti-de Sitter space, not the expanding universe we inhabit, but it showed the principle in action. Everything happening in a higher dimensional world could be fully encoded in a lower dimensional gravity-free theory. Physicists suddenly had a dictionary between worlds, and the black hole paradox began to look less like a dead end and more like a clue that space itself is not fundamental. Once locked in a public debate with Hawking about whether information was truly lost, found himself on the side that ultimately prevailed. In 2004, Hawking conceded, acknowledging that quantum theory's demand for information preservation could be reconciled if black holes somehow leak their secrets or never fully hide them. Holography offered a way out. The details of what falls in are not destroyed, but encoded on the horizon, later released as the black hole radiates away. But beyond technical victory, the picture is haunting. Imagine every star you see at night, every swirling galaxy, every black void, all of it folding gently onto an invisible sheet, a boundary that contains the full script of our universe. You could picture it like a vast map, light years across, but only one surface thick, holding patterns so dense and minute that they capture all the richness of three-dimensional life. Our reality would be like a grand cinematic projection, deep to us, flat in its true bookkeeping. In laboratories and chalk-filled offices, the holographic principle is more than poetry. It is a tool. String theorists use it to calculate properties of black holes and strongly interacting quantum systems. Condensed matter physicists borrow holographic duality to model complex materials. But for those who like to let the implications breathe, it is also one of the most radical shifts since Einstein, not just a new equation, but a suggestion that the universe is, at its core, informational. This brings us close to the frontier where physics and philosophy blur. If space and gravity can emerge from entanglement patterns, as some researchers propose, then perhaps geometry itself is built from relationships between bits of quantum information. The deep there-ness we feel, the sense of living in solid rooms under wide skies, might be a kind of mirage born from an underlying network. It does not make our world false. It makes it emergent, as sound emerges from vibrating strings or heat from molecules. But it changes how we think about ultimate reality, not things and places, but information and pattern. Picture the scene as though from outside. Stars wheel silently in blackness, their light ancient and cold. Slowly, they seem to stretch and flatten, their glowing arcs pulling toward some immense invisible surface. Galaxies shrink to filaments, and then to threads of code etched across a limitless skin. Even time feels as if it could be drawn out and stored. It is a difficult picture because we are inside it. We only know depth. Yet the math whispers that depth might be no more essential than the 3D image floating above a hologram. For the story of many worlds, holography adds another layer of wonder. If all possible quantum outcomes exist, and if the universe itself can be fully encoded as information, then perhaps each branch is simply another script written across some ultimate canvas, each as real and permanent as the data that defines it. In that way, the idea that we are shadows is not diminishment but inclusion. We are part of something vast enough to hold infinite variations, each secure in the silent mathematics beneath Leonard Susskind once said that physics is teaching us to be humble about what real means. Our sense of a single, three-dimensional, continuous world may be like a well-made illusion, precise enough to sustain us, but not the whole truth. And when you step outside on a cold night and look up, it is possible to imagine the stars not just burning in space, but folded somewhere onto a hidden sheet. Light turned to code, the entire sky already written before you lift your eyes. At first glance, the many worlds idea seems as though it should leave scars on experience. If every quantum event can branch reality, if coins and electrons, and even our own choices slide into separate histories, why do we not feel the fracture? Why does life seem so steady and whole, each moment stitched cleanly to the next? The answer lies in a process that is almost invisible, but relentless, a quiet mechanism called decoherence. It is not a force or a new particle, but rather the natural fading of quantum possibility. When a delicate system interacts with its surroundings, through decoherence, the shimmering haze of overlapping states collapses into what we call classical reality, though no conscious observer is needed and no mystical act of measurement takes place. Instead, the world itself, warm and busy and full of noise, is constantly measuring itself. Quantum objects begin in superposition. An electron can spin up and down at once, a photon can travel to paths at once, a molecule can spread like a wave through space. But the environment, air molecules, stray light, vibrations, even the cosmic microwave background is never truly absent. Each interaction, no matter how slight, entangles the quantum system with countless other particles. The fragile phase relationships that keep superposition alive wash out almost instantly. What remains is not a single outcome magically chosen, but a set of separate, non-interfering branches. Each branch carries a full record of events consistent within itself. We inhabit one because the others, once discarded, can no longer influence or recombine with our timeline. This may sound abstract, but in the late 1990s and early 2000s, physicists managed to watch it happen in the laboratory. Teams in Vienna and Paris began experimenting with large molecules, not just electrons or photons, but clusters of carbon and hydrogen called fullerenes. 60 or 70 atoms arranged in soccer ball-like cages. These molecules are enormous by quantum standards, nearly a nanometer across, heavy enough to feel almost tangible compared to a single electron. Researchers built matter-wave interferometers, sending fullerenes through ultra-high vacuum chambers, where they passed slits and diffracted like light. On a detector screen, an interference pattern emerged. Clear proof that even such large, complex objects behave as waves when protected from their environment. But the pattern vanished the moment stray gas molecules or heat or light touched the system. Decoherence had arrived, and the superposition unraveled into ordinary particle paths. The fullerene did not decide where to go. The surrounding world quietly made the many possible paths, distinct and unreachable from one another. You can think of decoherence like smoke curling in still air. At first the threads twist and overlap, delicate and reversible. Then, as they spread and hit moving air, the pattern snaps and breaks into disordered currents, each separate and untraceable. The quantum wave function begins as coherent smoke. The vast, noisy universe shreds it into pieces faster than we can blink. For tiny, cold, isolated systems, the smoke can linger and show its ghostly interference. For anything warm, wet, and alive for you, sitting at a table, decoherence is instantaneous and absolute. This is why you do not feel the split. Your body is an ocean of interactions. Photons striking your eyes, molecules jostling in your skin, thermal vibrations everywhere. Any quantum branching within you or around you becomes irreversible almost immediately. The alternate versions peel away with no communication left, like bubbles separating in still water. There is no moment of tearing, no sense of doubling. Your memories remain internally consistent because they are part of the same. Branches entangled record for Everett's interpretation. Decoherence provides the missing bridge between equations and experience. Everett knew the wave function never collapsed, but he lacked a mechanism to explain why worlds do not bleed together in ways we could detect. In the 1970s and 80s, researchers like H. Dieter Z. and Wojciech Zurek developed the theory of environment-induced decoherence, showing mathematically how contact with the wider world destroys interference and locks in distinct outcomes. They proved that observation does not require a conscious mind. It simply requires interaction and entanglement with enough degrees of freedom that coherence is hopelessly lost. The implications reach beyond philosophy. Quantum computing, for example, lives and dies by the battle against decoherence. Qubits can perform incredible feats of parallel calculation only if their superpositions remain intact long enough to finish the job. That is why quantum processors are cooled to millikelvins and shielded from stray signals. Engineers are trying to quiet the universe's endless, measuring just long enough to compute, yet even in the coldest, most controlled conditions, decoherence creeps in, turning quantum probability into classical certainty before tasks can complete. Error correction protocols and elaborate shielding are all attempts to hold off the silent divider. For ordinary life, though, this divider is a gift. Without it, the macroscopic world would shimmer and flicker unpredictably. Tables and chairs might remain in ghostly overlays. Cause and effect would break under the weight of uncollapsed waves. Decoherence gives stability without needing an observer to push reality into place. It lets a single predictable thread emerge from the quantum haze so that we can walk and speak and build. Imagine again, smoke. This time not in air, but in the vacuum chamber of a physics lab. A cluster of fullerene molecules drifts forward, its quantum waves swelling and splitting. For a brief, beautiful stretch, it is everywhere, exploring all paths at once. Then a stray photon from the warm lab wall touches it. Instantly, the delicate superposition crumbles. The interference fringes fade, the molecule takes one path, and any alternative universes drift silently away, sealed by loss of coherence. That same story happens around and within us billions of times each second. The world split. We remain unaware because the split is cleaner and faster than any possible signal. It is a strangely comforting thought. The universe may be unimaginably rich in branches, but the life you know is whole, because dicoherence protects its continuity. You are not haunted by flashes of other paths, because physics itself has drawn a curtain between them. All the while, in the deep quiet of matter, the branching continues endlessly, silent, invisible, and absolute. Long before we had the words to describe quantum branching or cosmic inflation, there was already something restless moving in us, a quiet pressure that asked what might exist beyond the edge of the known. It was not always about survival or trade. Sometimes it was only about the ache to see if another world waited just past the horizon. You can feel it when you read about the first ocean voyagers who left safe coastlines with no maps, certain enough to promise return. The Polynesian navigators crossing the Pacific thousands of years ago, reading swells and stars with a skill almost mystical, set out because somewhere beyond the breakers there had to be other islands. The same spirit lit the lanterns of 15th-century caravels as they slipped from European harbors, their decks crowded with sails and timber that creaked as if aware of the gamble. Sailors from Portugal and Spain steered into waters without reliable charts, driven by a mixture of hunger, ambition, and a pull deeper than commerce, the need to know what else is possible. That impulse, multiplied and refined, became the habit of whole cultures. It guided caravans across deserts, sent ice-hardened ships north toward invisible poles, and carried balloons and airplanes into the thin air above continents. Always there was a sense, however half-conscious, that the world might be larger, that another elsewhere might exist, and that reaching it would in some way complete us. Though they could not speak of parallel universes or quantum states, explorers carried the same refusal to accept one narrow domain as the entire story. By the 20th century, the reach of this instinct had leaped beyond Earth. Rockets rose first as weapons, and then, astonishingly quickly, as vehicles for leaving the planet itself. In 1977, NASA launched 2 spacecraft that embodied perhaps the purest expression of this urge yet. Voyager 1 and Voyager 2. They were not built to return or even to be controlled forever. Their paths were meant to take them past the outer planets and then outward without end into interstellar space. On board each spacecraft was a golden phonograph record, a small, careful offering for anyone or anything that might someday find it. Carl Sagan and a committee of scientists and artists curated its contents. Greetings in 55 languages. A selection of world music from Bach to Senegalese percussion. Sounds of surf and birds, and a mother's first words to her newborn. Images etched in analog grooves showing landscapes. DNA, human anatomy, photographs of people waving. The record was a fragile hope cast into the dark, a message across a multiverse we could not name, longed to reach. Voyager's golden record is not proof of other worlds, but it is proof of us. It says that even when faced with the immense silence of space, we could not help but send a greeting, an outstretched hand. The same voice that wonders if there are infinite versions of ourselves. Somewhere also whispers to the void, if you are out there. No, we lived. We thought. We tried to understand in 1990. Voyager 1, already billions of kilometers from Earth, turned its camera back for one last photograph before shutting down most of its instruments to save power. The result is what Carl Sagan named the pale blue dot. In the image, Earth is nothing but a tiny speck suspended in a shaft of scattered sunlight, less than a pixel wide. Sagan's reflection on that photograph still cuts deep decades later. That's here. That's home. That's us. Seeing ourselves so small did not end the hunger to explore. It sharpened it. If our entire known life can be reduced to a mote of dust in a single beam of light, then what other motes might exist? What other lights might hold worlds and beings we can only imagine? It is not an accident that these feelings echo the logic of the multiverse. Long before physics proposed infinite branches or eternal inflation, we felt incomplete without the unknown. We sent ships out not only to map coastlines, but to test whether our reality could be bigger than the single safe bay we knew. We build telescopes to stare deeper, not just for knowledge, but because something in us refuses to stop at one sky. The many worlds idea, though technical, is a scientific form of the same refusal. Perhaps there is more than this one path. Perhaps existence itself is wider than we thought. Picture a harbor at night, hundreds of years ago. Lanterns swing from the sterns of wooden ships as they slide from the quay, masts tilting against stars. Families watch from the docks until the lights are only pinpricks on black water and then nothing. That scene is not so different from a rocket lifting into the dark, its flame dwindling to a point before it vanishes beyond vision. Both are gestures of curiosity, of hope, of a certain loneliness. Now imagine pulling back far enough to see those lights disappear entirely. The ocean gives way to the curve of Earth. The ships and rockets become dust against the sea and sky, and still the searching goes on. Somewhere beyond the heliopause, Voyager travels in silence, carrying a tiny spinning record that may drift for 1 billion years before another intelligence, if any exist, ever touches it. Its path is a human thread thrown into a vast, unmeasured expanse. An act of faith that somewhere beyond our known branch of reality, something waits. Or at least listens. Our technology changes, but the impulse remains constant. We voyage because staying still feels incomplete. We build instruments because silence is too narrow. Whether we speak of other continents or other universes, the root is the same hunger to look past the edge of the map and say, there must be more. In that sense, the multiverse is less a new concept than a scientific echo of a very old human truth. We have always been willing to step into darkness for the hope of another shore. So when you think of infinite worlds, do not picture only equations in physics. Picture ship lanterns fading into black water. Picture a tiny golden record sailing beyond the sun. Picture a pale blue dot caught in a sunbeam 40 astronomical units away. These are the physical footprints of the same restless longing. The search for elsewhere is not just about where we might go, but about understanding who we are, a species built to wander beyond its single world. Even if the road leads into silence, science advances with proofs and measurements. But it also advances with questions so bold they almost seem like trespasses. And nowhere is that more visible than at the edges of quantum theory, where the multiverse lives. The many worlds idea is difficult, not because the mathematics fails, but because it refuses to give us any way to peek across the divide. Each branch is sealed, decoherence complete, leaving us inside one story with no bridge to the others. Yet for decades, some researchers and dreamers have tried to imagine how we might at least test the edges of that barrier, how we might catch reality in the instant before it decides. They know the effort may fail, but they keep working because the possibility of seeing the split of touching, the place where worlds diverge, is too compelling to ignore. Among the most haunting of these proposals is the so-called quantum suicide thought experiment. It is not a test anyone should ever attempt. It was always meant as a brutal mental exercise rather than something to enact. The idea was first framed clearly by the cosmologist Max Tegmark in the late 1990s to explain what the many worlds interpretation would mean if taken seriously. Imagine a device rigged so that each time you press a trigger, it measures the spin of a particle. If the spin is up, nothing happens. If down, the device fires instantly and fatally. Quantum theory says the spin is in superposition until measured. In Copenhagen's view, one outcome is chosen randomly and you might die half the time. In Everett's view, the universe splits. In one branch, you are unharmed. In the other, you are gone. From the perspective of the surviving observer, the act would always seem safe. You would only ever find yourself alive, no matter how many times you tried. It is an unsettling illustration, used to show how probability and personal experience diverge in a multiverse. But it also highlights why these ideas remain philosophical. The cost of an actual experiment would be fatal. The logic holds only on paper. Less morbid and more practical are attempts to probe. Wave function collapse directly to see whether the universe really does make a single choice when quantum systems grow large enough. One path into this is the family of delayed choice experiments, first imagined by John Archibald Wheeler. Wheeler asked, what would happen if you decided how to measure a quantum particle only after it had already traveled part of its path? In the famous double-slit experiment, for instance, light acts like a wave if you do not check which slit it goes through, and like a particle if you do. Wheeler proposed waiting until after the photon has passed the slits to choose whether to detect its path. Astonishingly, experiments built on this idea show that the photon's behavior seems to adjust retroactively, as though the decision of how to measure can rewrite what happened. Modern labs have performed such tests with fast optical switches and entangled photons, and though they do not prove many worlds, they confirm that the quantum world does not respect simple cause and effect in laboratories across the world. Researchers continue to build ever more delicate setups to watch coherence decay and interference fade. They use ultra-cold atoms, superconducting circuits, and even mirrors so sensitive they can recoil from single photons. Their goal is to catch a quantum system in the very act of losing its superposition, to map exactly when and how the classical world emerges. None of this opens a window to other universes. Decoherence still seals the branches. But each experiment sharpens our understanding of the boundary and tests whether collapse is fundamental or only apparent. Some dream that if collapse were real, if something beyond decoherence picks a single outcome, we might find it and measure its signature. Others hope to prove no such collapse exists and so strengthen Everett's endless branching. These experiments rarely look dramatic. Imagine a dark vacuum chamber the size of a small car, its polished metal sides lined with feed throws and wires. Inside is near-perfect emptiness. A few atoms float, controlled and measured by lasers that flicker in precise pulses. Outside in the control room, computers hum softly, while oscilloscope traces ripple and fall. LED indicators blink red and green like quiet stars, marking each event: a photon detected, a qubit flipped, a mirror moved by the push of light. There is no roar or flash, only the still patience of people trying to listen to nature at its most secret. The debates surrounding these efforts are as lively as the experiments themselves. Some physicists argue it is misguided to talk about testing the multiverse at all. Many worlds is simply a different interpretation of the same equations, and therefore produces no new predictions. Others counter that, while direct contact with other branches seems impossible, clever indirect evidence might still appear perhaps in unexpected correlations, or in proof that collapse theories fail in every regime we can reach. The argument is not only technical, but emotional. For some, the elegance of Everett's view is irresistible. No special magic, just equations unfolding. For others, the cost, infinite unseen realities, feels too high, and they search for a simpler, single-world explanation, even if none has yet succeeded. What is striking is how even the most skeptical scientists allow themselves, sometimes, to wonder. Late nights in those quiet labs, a researcher adjusts a laser or checks data and feels the pull of the question: am I watching a single world cohere, or am I one thread among countless? The blinking lights on the racks are not just instrumentation. They are markers of the boundary between the measurable and the vast unknown. The people who work there know they may never break that boundary. Yet they keep building, pushing, inventing, because to stop would be to accept too easily the idea that our universe is sealed and simple. This edge of science work is not a rebellion against rigor, but a continuation of it. Each generation tries to push the frontier a little further, to see if reality will yield some new sign. Sometimes all they find is confirmation that the strange rules hold. Superposition persists when isolated. Decoherence kills it when touched. But in that patient mapping, there is a kind of courage, a willingness to stand near the deepest mystery and not look away. The multiverse may remain unreachable, but the act of trying to glimpse it, even with thought experiments as unsettling as quantum suicide, or with lasers timed to impossible precision, keeps alive the human desire to know how far existence really goes. And perhaps that desire itself is the surest sign that whatever the universe is, it is not small. Long before laboratories cooled atoms to near absolute zero or satellites, mapped the faint glow of the Big Bang, Human beings were already building universes beyond their own with nothing but words and imagination. The instinct to multiply worlds runs deep in us. It has lived in stories since the first voices gathered around firelight. When science seemed reluctant to wander past a single reality, art did not hesitate. Writers, poets, and later filmmakers stepped into the spaces physics left blank and filled them with daring possibilities. And in doing so, they kept alive the thought that reality might not be singular. One of the most haunting early explorers of this idea was the Argentine writer Jorge Luis Borges. In 1941, in his story The Garden of Forking Paths, Borges pictured time not as one line but as a labyrinth of diverging and converging futures. Every choice, every possibility, he suggested, is taken, each creating its own new path. Borges wrote long before Everett formalized many worlds, yet his vision feels like an imaginative rehearsal for quantum branching. In another story, The Library of Babel, he imagined an infinite library containing every book that could ever be written, every sequence of letters possible, meaning every life, every universe, already described somewhere on the endless shelves. He did not use the word multiverse. He did not need to. His metaphors opened the door as science fiction grew into a genre in the 20th century. The theme deepened and diversified. Writers such as Philip K. Dick filled pages with alternate timelines and unstable realities, where characters slip between worlds, or awaken to discover that the world they know is only one layer among many. Ursula K. Le Guin played with simultaneous futures and psychic crossings. Television and film turned these possibilities into vivid, shared dreams, episodes of The Twilight Zone showing doorways to other dimensions. Later series like Fringe and Dark exploring parallel lives with the seriousness of detective work. Marvel Comics and films made multiverses a cultural household word, turning physics' most speculative idea into blockbusters where different selves meet and worlds collide. The costumes and battles are fantasy. But behind the spectacle lies a seed of Everett's lonely proposal from 1957. It's finally embraced and loved by millions. This cultural undercurrent matters more than it first appears. Science does not grow in a vacuum. It grows in the soil of human curiosity and daring. Many physicists of the current generation admit they were first drawn to questions of space and time not by textbooks but by novels, movies, and the half-terrifying thrill of an infinite cosmos glimpsed through story. Fiction gave permission to wonder beyond what could be proved. It held the question open when formal physics turned pragmatic and cautious. Without that imaginative reservoir, ideas like the multiverse might have withered under academic suspicion. You can see this interplay if you look closely at certain breakthroughs. When Hugh Everett's Many Worlds paper was largely ignored, it survived partly in the hands of a few theorists, but also in the pages of science fiction. Where writers found narrative gold in the concept of endless branching, the culture of curiosity meant that, when experimental quantum work advanced decades later, the term many worlds already had a place in the public mind. When Alan Guth's Eternal Inflation suggested infinite bubble universes, it resonated because stories had long taught us to dream of other Earths. Even popular culture's playful versions, like Marvel's sprawling multiverse, give shape to the unimaginable, helping laypeople and scientists alike picture abstractions with emotional weight. To imagine this influence, think of a library stretching into mist. You walk between towering shelves that seem to have no end, their spines labeled in languages you know, and countless ones you do not. Somewhere on these shelves is the book of your life, as you have lived it, but also volumes where you chose differently, where history twisted another way, where even physics rewrote its laws. The library is impossible, yet it feels intuitively right. Borges taught us that, and in a way, modern theoretical physics is wandering those same aisles. Searching for the deeper catalog behind what we call reality, visual storytelling adds another layer. Films show characters stepping into other versions of themselves and force us to face the shock of identity not being singular. Audiences grapple with questions scientists also face. If there are infinite selves, what makes one life matter? If every choice is taken somewhere, does responsibility fade or deepen? These emotional rehearsals prepare the ground for genuine scientific courage. A physicist proposing multiple universes is less alone when the culture already understands the metaphor, in quiet ways. Fiction also shapes experiment. The dream of traveling between worlds fuels the determination to test quantum foundations, to probe decoherence, to build ever more isolated systems where superposition can survive. Engineers in cryogenic labs may not believe in superhero universes, but many grew up with science fiction that celebrated strange possibilities, and that inheritance makes them bolder. It is easy to dismiss pop culture's wild timelines as distraction, yet they play the same role myths once played for ancient sailors, maps of what might lie beyond the edge. Before telescopes, before compasses reliable enough to risk a voyage, sailors told each other stories about distant shores and unseen monsters. Those stories were wrong in detail, but vital in spirit. They built a tolerance for the unknown. Today, when we imagine multiverses through novels and films, we are building the same tolerance, readying ourselves for ideas that shatter the tidy room of a single world. So the next time you see a comic hero step into another timeline or read about an infinite library, you are watching humanity practice. We are rehearsing wonder and preparing to accept that reality could be stranger than comfort allows. The scientists who fill chalkboards with equations and cool qubits until they almost stop may not cite Borges or Marvel in their papers. But somewhere those stories help teach them that curiosity is bigger than fear. And perhaps that is what art and story have always done, kept alive the vision that existence can fork and multiply, that beyond the visible shelves there is more, and that walking toward the fog is a worthy thing to do. When people first hear the suggestion that there may be infinite versions of themselves, lives repeating and diverging across unseen worlds, the first reaction is often wonder, but soon after comes unease. If somewhere there is another you who made the right choice when you failed, or who failed where you succeeded, what becomes of responsibility? If each fork creates its own history, what does it mean to live well in the one you feel? These questions are not abstract puzzles, but human ones, woven into the quiet hours when we think about love lost, friendships broken, or moments of courage and fear. The multiverse, when brought close, does not stay in chalk marks on a blackboard. It steps into the kitchen, into memory, and asks how you hold meaning when the path is no longer unique. Imagine something as small as a word spoken in anger. In one branch, you apologized before the night ended, and the friendship lived. In another, you stayed silent, and the distance never closed. Both are real if the many worlds idea is right. Does that lessen the weight of what you said? Or does it deepen it, because somewhere there is also a version of you still carrying that silence? Some philosophers argue that branching does not absolve. It multiplies. Your choice still defines the story you are living. The fact that other versions chose differently does not repair the hurt felt here, between these two people in this specific world. It simply means that regret has company you cannot meet. Love, too, becomes more intricate under infinite skies. Perhaps you wonder about the person you almost stayed with, the move you almost made, the letter you almost sent. In the multiverse view, those lives do exist, humming just beyond reach. Filled with ordinary days of togetherness or solitude depending on the branch, but this does not make the love you hold less real. If anything, it clarifies that love is not about being the only possible outcome. It is about being the one you inhabit and tend. The garden you plant matters, even if other gardens bloom elsewhere. To know that some other self might be happy or lonely does not change the work of caring here. And now, forgiveness takes on a strange light as well. If you have been harmed, does it help to think that somewhere or another you was spared? Some find it comforting to picture a self who avoided pain, but for others it sharpens the sting. Why not me? Why that one? Yet forgiveness has always been an act of choosing peace in the only world we can touch. Even if branches sprawl beyond sight, the person across from you is still singular. Their remorse or indifference is still real and cannot be borrowed from another timeline. To forgive remains a local act, quiet and personal. Chance, too, becomes more mysterious. We are used to thinking of fortune as a roll of dice, but in a multiverse, every roll happens. The version of you who survived the accident, found the job, met the friend, lives alongside one who did not. Does this make gratitude smaller or larger? Some find it enlarges it, to know that the life you wake to is one of many possible, and yet it is. Yours can bring a fierce tenderness to ordinary mornings. Each breath feels like a path taken when so many diverged. Philosophers sometimes call this view modal realism, the idea that all possible worlds are as real as this one. But for non-philosophers, the question is simpler. How do we keep our lives meaningful if we are not alone in possibility? The answer, quietly, is that meaning has never depended on uniqueness. When you hold a child's hand, write a letter, plant a tree, the worth of that act is in its living presence, not in whether it happens nowhere else. Even if infinite selves exist, none of them cancels the heartbeat you feel right now. Ethics in a branching cosmos may even be more urgent, not less. If actions split worlds, then every choice is a kind of creation, a making of new histories. You cannot rescue the version of a friend hurt in another branch, but you can shape kindness here and trust that kindness echoes in other directions as well. The vastness does not absolve. It invites carefulness, because possibility is no excuse for harm. Picture a quiet room where two people sit across from each other, candlelight trembling on their faces. Outside, it is night and rain clicks against the glass. Somewhere in the unreachable elsewhere, there are countless other versions of this moment. Somewhere apology came sooner. Somewhere anger still burns. Somewhere love was spoken aloud. But here, in this single room, two hands edge closer across the table, almost touching. Whatever multiverse sprawls beyond, only this hand can be reached. Only this silence can be broken. The rest is invisible, and for living, irrelevant. In this way, the multiverse can feel less like a threat and more like a backdrop that humbles and enlarges life. It says our world is not the only stage, but it is still a stage where real things happen. It says regret is natural, but not binding. Because while you cannot slip into the life where you made another choice, you can still make new ones here. It says love matters not because it is rare, but because it is lived. Meaning never came from being the sole version. It came from being present and responsible in whatever version you wake to. So when the idea of infinite selves feels dizzying, it may help to step back from cosmic scales and remember the immediate, the room you are in, the breath you take, the person you might choose to reach for. Other worlds may be countless, but they are closed to you. This one is not, and its nearness is enough to fill a life with purpose, even against the backdrop of infinity. At mountaintop domes and in long, dry valleys where the air is thin and still, humans build machines to listen to the oldest and faintest signals the universe can send. The dream driving these observatories is older than any telescope, to know whether the cosmos we see is all there is, or only one part of something immeasurably larger. In recent years, that dream has turned toward a specific and haunting possibility that if other universes were born, if space itself has bubbled and cracked and begun again, the marks of those events might still drift through the void. Not in light we can see, but in ripples of space-time and patterns of ancient radiation too soft for ordinary senses. But perhaps not beyond our reach in the deserts of Hanford, Washington, and the pine woods near Livingston, Louisiana. Two great L-shaped instruments stretch across the ground, the Laser Interferometer Gravitational Wave Observatory, better known as LIGO. Each arm is 4 kilometers long, lined with vacuum tubes and mirrors, polished until they are nearly flawless. LIGO was built first to detect gravitational waves from colliding black holes and neutron stars, and it succeeded spectacularly, catching its first signal in September 2015. A faint chirp from a pair of black holes merging 1.3 billion light-years away. But beyond that triumph lies an even bolder hope. If our universe ever bumped another during its inflationary youth, if there were other Big Bangs leaving behind their own expanding bubbles, then the collisions might have shaken space-time itself, launching waves that still move through us. These waves would be different from those LIGO first captured, older, broader, too deep for a single event's quick chirp. Detecting them would mean hearing, quite literally, the breath of other universes. To hunt those whispers, scientists push for even greater sensitivity. They plan detectors like Cosmic Explorer in the United States and the Einstein telescope in Europe, with arms 10 times longer, or with underground placement to escape noise. Meanwhile, another set of eyes or ears works in the cold vacuum of space. The European Space Agency's LISA mission, now in development, will send 3 spacecraft flying millions of kilometers apart in a triangle, their laser beams forming an immense interferometer that can sense slower, more ancient waves than LIGO can catch. Together, these instruments hope to open a new window, not on stars, but on the very birth of space and time. Light, too, is still a messenger. Though so stretched and cooled by age that only specialized instruments can read it, the cosmic microwave background remains the oldest photograph of our universe, a baby picture from about 380,000 years after the Big Bang. Within its tiny temperature, ripples might be scars left by a universe brushing another, or by gravitational waves from primordial expansion. Telescopes on the ground, like those at the South Pole, and in space, like the upcoming Light Bayard mission from Japan, aim to trace the polarization of this light, subtle swirls that could reveal the tremors of inflation or collisions beyond. Each new map is a search for faint fingerprints at the edge of KNOWABILITY. At the same time, telescopes like the James Webb Space Telescope look forward rather than backward, but their gaze may still brush the question. JWST peers at the first galaxies and stars, hoping to understand how structure formed after the Big Bang. If our cosmos once rubbed shoulders with another, if the physics of our bubble was tilted or scarred by some older meeting, the imprint might show in how the earliest galaxies gather and shine. These are delicate, almost poetic hopes, that by measuring light from 13 billion years ago, we might catch the echo of a cosmic neighbor we'll never meet. To stand in one of these control rooms is to feel both the vastness and the fragility of the search. Banks of monitors glow in the dark, while outside the air is so still you can hear your own breathing. Inside the vacuum tubes of LIGO, laser beams bounce thousands of times between mirrors before returning. Their paths, so stable they can detect distortions smaller than a proton's width. The scientists know what they are doing is improbable, yet each detection so far, first, the black hole merger, then neutron-star collisions, has taught them that improbable signals can still be caught. The instruments work. Space-time can be heard, and so the search for something deeper goes on. Some are looking for a stochastic background, a faint, steady hiss of gravitational waves from events older than galaxies. Others search for specific bursts that might mark the collision of vacuum domains in an inflating multiverse. No one can say if such things are truly within reach, but the fact that we can even imagine listening for them is itself astonishing. The night sky above these machines is cold and apparently silent. Yet the scientists working there often describe it as alive with hidden tremors. They know that every star we see is also shaking space-time as it moves, that every massive event ripples through the cosmic fabric. The hope is that among those countless ripples is one older and stranger, the signal of a universe's birth or brush with another. If ever we catch it, the discovery would not just change physics, but alter how we see the night, no longer empty. No longer a solitary dome, but a place alive with unseen company. Picture it. Starfields trembling so slightly, we cannot sense it. Dark matter halos swaying under invisible waves. Detectors deep on Earth and far in space waiting for a twitch of distance measured in fractions of a proton. A sky that will never be empty, because every moment it is alive with echoes of things older and grander than our whole. Milky Way. We may stand on one small branch of reality, but above us, the darkness may still carry the breath of other beginnings, faint as whispers, but patient. Waiting for the day our ears grow sharp enough to hear, it begins so quietly you almost forget it is happening. You stand somewhere ordinary in a kitchen, on a sidewalk, maybe alone on a late-night train, and a small decision moves through you. Do you call? Do you turn back? Do you stay silent? It feels like nothing, just another moment in a long chain of them. But if the physics we have followed is even close to true, something vast unfolds at that point. Each breath, each blink, each nerve pulse is tangled in quantum events, electrons shifting, molecules exchanging energy, photons scattering. When those events interact with the huge, noisy world around you, they cannot hold their fragile superpositions. They decohere, they settle into facts. But the settling is not one road closing and another fading. It is a quiet splitting, 1,000 rooms opening where there seemed to be one. You do not feel it. Decoherence is too fast, and your senses are tuned to continuity. Yet the thought that your life is not a single thread but one among a limitless tangle grows harder to ignore once you have seen how reality works at its smallest scales. You may never sense the other rooms, but you know they exist. Filled with selves who turned left instead of right, who spoke, who stayed silent, who loved or walked away. They are not ghosts, and they are not accessible. They are sealed as cleanly as dreams when you wake. Still, they are there. The mathematics says so. Their presence changes how the moment feels. It can be frightening at first to think this way. Infinity carries weight. But then something else happens. The fear turns to a kind of quiet awe. You realize that the universe is not brittle. It does not collapse into one fragile story that can be ruined. It is rich and branching and generous. The fact that you cannot move between the branches does not mean they are wasted. It means that every version of you is real enough to deserve a world. Every world is stable enough to hold whatever love or loss lives there. Far from making life meaningless, it gives meaning room to breathe. When you reach back into memory, the mistakes and regrets shift slightly under this light. They are still yours. They still have weight. But somewhere, there are versions of you who chose differently. And somehow, that knowledge softens the sting without excusing it. It reminds you that choice is alive and fragile and not bound to perfection. You cannot change past branches, but you can shape the one you are on now. Every breath is still a door. Every ordinary act can unfold in countless ways. Think of something intimate, a quiet apology waiting in your throat, a message you could send or delete, a promise you could keep or break. In one direction, the air cools and distance grows. In another, warmth returns, however slowly. The many worlds picture suggests both futures are real, but only one will become the life you know. That is not a reason to despair. It is a reason to move carefully and kindly. Your choice writes a whole reality. Even if countless versions exist, the one you inhabit matters because it is the only one you can touch, at the edges of physics. The language grows cold and exact. Hilbert spaces, unitary evolution, quantum states. But standing here, thinking about your own life, the mathematics becomes a kind of poetry. You are a point where lines diverge. Your every small act helps shape the texture of an entire universe. And although you cannot watch the other threads unspool, you can sense their presence like rooms beyond a closed door, each full of other mornings, other faces, other chances. Outside, the night sky stretches in its silent immensity. You know now that it is not empty, not just because of stars and galaxies, but because space itself may carry echoes of other births, other beginnings. You stand under that sky and feel a strange steadiness. You are small, yes, but also part of something endlessly fertile. The fear of choosing wrong loosens its grip. You cannot destroy possibility by living. You are part of it. Imagine walking down a hallway that seems at first to have only one path. Slowly you notice faint outlines of doors to either side. Not doors you can enter, but signs that there is more beyond the walls than you guessed. At the far end, a single door stands open, light spilling through so bright it washes the corridor in pale gold. You step toward it, aware of the infinite rooms you will never see, but comforted by their presence. The path you walk is enough. It is alive and vast, because the universe itself is alive and vast. If there is a lesson in all the theories and the experiments, it is not that life is meaningless. It is that life is uncontainable. Reality refuses to be small or final. And so the right response is not fear, but humility, and maybe gratitude. You are one thread in a pattern that will never end. You are also the weaver of this thread. Here and now, as the light at the hallway's end grows closer, you realize that nothing has changed and everything has. The kitchen is still a kitchen. The train is still a train. The sidewalk still smells of rain. Yet each breath is enormous now, each heartbeat a quiet branching. You step forward, not into confusion, but into wonder. The sky above you is full, the doors ahead uncountable. And somewhere in that fullness you keep walking, awake to the vastness and at peace with your single, precious road.